After photoelectric effect, Compton effect was another phenomenon that again confirmed the corpuscular or the particle-like behavior of light. This experiment was first done by Compton himself. What he did in his experiment was he used a X-ray source. The emitted X-ray is defined for a particular lambda only, or we can say that the X-ray source is perfectly monochromatic. So he used a scatterer that is a graphite crystal. So like X-ray incident rays incident on this scatterer, and the waves are scattered. So he observed the scatter waves. What he saw is that he draw a intensity pattern with respect to the wavelength. He saw that intensity is reached the peak value at for two particular wavelengths. So first wavelength is the same as the wavelength of incident X-ray, and the second wavelength is shifted a little bit amount from the original wavelength. We can call it del lambda. He observed in his experiment that this del lambda is dependent on this angle theta. Theta is the angle at which we look at the scattered waves. So before going to the theory that experiment derivation that Compton gave, which perfectly described this observed intensity pattern, we will look at the original classical theory of scattering, which was given by Rayleigh. So we call it Rayleigh scattering. According to Rayleigh, at that time light was considered to be waves only. So these waves are incident on the scatterer with a particular frequency and with particular energy. So what the light waves does to the scatterer atoms of the scatterer is that it causes oscillating accelerations to the electrons of the constituent atoms. So after the light is incident on the graphite crystal, the electrons started oscillating, and this oscillating motion is giving rise to the after this electrons started oscillating, that is kind of accelerations too. So we know that accelerating electrons can emit electromagnetic waves. So this frequency is the same as the frequency of the incident light. So the emitted finally emitted electromagnetic wave from the oscillating electrons is the same as the frequency of the original wave. So we should get only the peak at the original wavelength or the original frequency only. So we shouldn't have got this other peak according to the classical theory of Rayleigh. But I would like to note here that Rayleigh scattering is valid for macroscopic particles. So if you look at anything, means any bigger particles or any bigger matters, Rayleigh scattering is valid. Or if you be precise, if lambda tends to infinity, Rayleigh scattering dominates. Now we will look at the theory given by Compton to describe the practical results of his experiment. For that we will have to look at consider theory of relativity as well as the theory of quantum physics as given by Max Planck, where he considered energy to be discrete. So energy of a system will be nhν, where h is the Planck constant and nu is the frequency of the light. We can consider n to be 1 here, so it will be hν. I mean the energy is nhν, but difference of the energy of two levels will be hν. So this is del E only, but we are writing E here. So E is not the energy here, but this is the energy difference. Okay, now we are considering photon to be a bundle of energy. So if a photon is moving with a velocity v and thus has a race mass m, its energy should be m naught c square 1 by v square c square. As the velocity of photon is equal to c, so energy will be infinity, tends to infinity here, but it is not the case. Energy is finite, is equal to h nu, so we can conclude that the race mass of photon is equal to 0. So we are considering another equation here, that the relation of the race mass and the momentum of a particle with the total energy. This is the race mass energy, and this is the energy corresponding to the momentum. So here the race mass energy of photon is 0, so this term is this will be square, this term is neglected, so equals Cp, again P equals E by C, and we have seen E equals h nu, so it's nu by C. Now one more thing, Compton assumes something in this derivation, is that as we have seen that the scattered waves are independent of the material, that is graphite, as he had used in this experiment. So the scattered waves are independent of the characteristics of or properties of graphite. So he has concluded that this scattering process doesn't involve the whole atom, it just involves the electrons, that to the free electrons. But as we know, the electrons are bounded to the atoms, so like free electrons are, the concentration of free electrons very low in case of graphite. So but it is justified because that the nu of X-ray is very high, so energy of h nu is very high. As we had seen in the photoelectric effect, the ultraviolet rays already enough to take out the electrons from the bound state. So nu of that is the frequency of X-ray is already very higher than that of the ultraviolet rays, so energy in this case is very much higher than the ionization potential of electrons. So we can consider the electrons to be free in this case. So electrons are free in this case, and like this whole process is the process happens between the photons, the particles of light and the electrons. So the photons comes and it collides with the electrons in the graphite, and the whole process continues. Here we have drawn two figures describing the collision between the particle of light, that is photon, and a free electron, and these electrons are once again assumed to be stationary. And we have seen that the we have drawn it in x-axis, we have assumed for simplicity the photons are moving in the positive x direction, it collides with the electrons and again after that electron is scattered with angle phi from the x-axis, and photon is deflected from his original path by an angle theta. Here we like if the mass of electron is m naught, mc square is the race mass energy of electron. Originally the energy of photon was E naught and its momentum was P naught, and after the scattering the new energy of photon is E1 and its new momentum is P1, and again the kinetic energy of electron is K here, and its race mass will be same as mc square. So what we do here is that we apply the law of conservation of momentum first. Like if we apply law of conservation of momentum in the x-axis, we will have p naught, that was the momentum of photon before the collision. After the collision, in x-axis, if we write the component of the momentum of photon and electron in the x-axis, like we write the momentum of electron to be p here. So it will be p1 cos theta and p cos phi here. And if we apply, it was before and was after the collision, and if we apply the law of conservation of momentum in the y-axis, it will be component of p1 along y-axis equals component of p along y-axis, that is p1 sin theta equals p sin phi. So if we write p1 and p naught in one side, means the momentum of photon in one side and momentum of electron in the other side. p1 cos theta squaring it, p square cos square phi, and again this equation will become 1 square sin square theta equals p square sin square phi 1 and 2. After adding these two equations, we will get p naught square p1 square minus 2 p naught p1 cos theta equals p square as equation 3. Now we consider the law of conservation of energy for the whole system. So before the collision, energy of photon was E naught, and race mass energy of electron was mc square. Race mass energy of photon is 0 and electron was at rest, so it didn't have any kinetic energy. After the collision, the new energy of photon is E1. The new race mass of energy of electrons will be same as the before, and the new kinetic energy of electrons will be k. So we can write is E naught minus E1 equals k. So as we had already derived that E equals or P equals E by C, so we can write here is that E naught in terms of P, so it will be C into P naught minus C into P1. So C P naught minus P1 K. So we will have to use this relation after. So now the whole we will consider the total energy of electron here. So like K is the kinetic energy and m naught c square is the total energy of electron. So we square it, like we had already got this relation, m naught c square whole square plus c square p square. The p is the momentum of any particle. So E is k plus m naught c square here, and m naught c square will be same here, and c square p square will be there. Now we like this will be equals to k square plus 2 k m naught c square. This term will be cancelled out, c square p square. So after, now we will put the value of k in this equation that we got from this equation, that is c square p naught minus p1 whole square 2 into k naught is again c into p naught minus p1 and m naught c square p square. Yeah, c square will be cancelled out. Now writing p naught square plus p1 square into 2 into c m naught p1 square and p1. This will give, wait, yeah, we will have to, like, this is equal to p square. Again we will replace the p square from another time, the p square that we had got from the law of conservation of momentum, that was this term. So we'll write that p naught square equals p1 square plus 2cm naught p naught p1, also p1. Then instead of p square we will write p naught square plus p1 square minus 2 p naught p1 cos theta. There should be 2 p naught p1 term plus 2 p naught p1 term. So after that we will get these two terms will be cancelled out. There will be a p naught p1 term, so 2c m naught p naught minus p1 equals p1 p naught. 2 will be cancelled out. 1 minus cos theta. So we can, if we modify these terms, we will get 1 by p1 minus 1 by p naught equals 1 by m naught c 1 minus cos theta. And if we multiply both sides with h, that is h by p1, h by p naught, h by m naught c 1 minus cos theta. This will be the wavelength from de Broglie equation, h lambda 1 lambda naught. This is another, this dimension of this is also lambda, wave equals to wavelength. We can write it lambda c 1 minus cos theta. The mass is the mass of electron. If we this is the velocity of light, this is the Planck constant. If we calculate all these things, we will get that lambda c equals 0.0243 Armstrong. So here, what is this? Lambda naught is the original wavelength of the X-ray. This was the new wavelength. So this is nothing, just the change in the wavelength. So it equals to lambda c 1 minus cos theta. So we have seen that this wavelength shift of the Compton effect that we had shown in the graph, that it was like something like this. It depends on the angle at which we look at the scattering waves, so that is angle theta. So we, like, using the quantum mechanics and the idea of corpuscular model of light, Compton was able to prove his experimental results. So one more thing I would like to say are that we have only till now we have only explained why we get the wavelength shift, but we haven't yet described why we get the original wave, like in the same wavelength as the incident wave. So, like we have in this the whole derivation, we had assumed that electrons are free here, but in reality not the electrons are free electrons, means some of the incident photons have less energies, for that it is not able to take out the electrons from the bound state. So in the derivation, del hc equals h by m naught c 1 minus cos theta. So in that case, m naught is the mass of, not the mass of the electrons, but is the mass of the whole atom, because the here the electrons is bound to the parent atom, so this whole atom is act as a particle here, so it is the mass of the whole electron, sorry, the mass of the whole atom. So that this term will be go very low, so Compton's shift will tends to 0, almost tends to 0. So for if m naught is like, if in place of m naught there is the mass of the whole atom, so this Compton's shift will go immeasurably slow, so we will get the peak at the original wavelength only. That is the case of the Rayleigh scattering. So in case of lambda goes to infinity, infinity, that is nu goes to 0, I mean very low, so energy becomes very low, so electrons are not free in this case for low energy photons. So that in that case, in the formula of Compton effect, in place of m naught the mass of the atoms only comes, so wavelength shift is very low, so we get the peak only in the incident wave only, incident wavelength only. So if wavelength is small, the Compton effect dominates, and if wavelength is tends to infinity, the Rayleigh scattering is dominated. So it is everything related to the Compton effect.